In this video, we're going to go over section 9.1, Introduction to Probability. So first, let's define what is a sample space in an event. A process is going to be called random if one of the outcomes from a certain set of outcomes is sure to occur, but it's impossible to predict with certainty which one. So as a definition, a sample space is going to be the set of all those possible outcomes of a random process. And an event is going to be any possible subset of that sample space. So some examples of that will be like, consider the sample space of tossing a coin. So when you toss a coin, you only have two possibilities. You get heads or tails. When you roll a die, let's think about a die with 6 faces. Then you're gonna have the opportunity to get the numbers from 1 to 6. If you're drawing a card, then your sample space is gonna be all the 52 cards, because getting cards from that is gonna give me 52 different possibilities. Now, the probability is governed by something that is called the equally likely probability formula, which is essentially if S is a finite sample where all the outcomes are equally likely, and then we have an event that belongs to the sample space, then the probability of the event is given by the number of times that the event occur over the number of elements on the sample space. For example, if we're going to draw one black face card at random from a deck of 52 cards, then my event is just going to be all the possible black face cards. So the J, the Q, the K for these two different suits, right? And now in total we have 6 possibilities. Notice here the event consists of 6 possibilities. But the sample space is going to be 52 cards. So my probability for this particular event of getting a one black face card is going to be 6 out of 52, since I have 6 chances to get one black face card out of 52 possible cards. So that probability is going to be around 11.5%. Okay. So let's check another example with rolling a dice. Let's assume that we have a couple die. One blue and one gray die, and each outcome is a pair that I can call B, G, where B and G are gonna come from 1, 2, 3, 4, 5, 6. Now, the total number of possible outcomes is gonna be 36, equally likely, since there's no better, one die is not gonna have better probabilities than the other. And let's say we get an event where we're considering that the sum is equal 7, the sum of the two results on the die. So the event, the pairs of that event will be given by pairs like 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Notice that the sum of those entries is going to give me 7. Now, how many do I have? I have 6 possible in this case that give me some 7. Out of possible 36 likely outcomes. That's going to give me the entire space. So, of course, this is going to be 6 out of 36 in my probability, and that's 1 over 6, which is the 16.7%. Now, I can think about a different sum, like if I do sum 2, my event is going to be completely different. The only one that gives me sums 2 is the pair 1, 1. So the probability of sum 2 is going to be 1 over 36, which is 2.8%. So it's not like always is going to be 6 entries. You can have completely different sums depending on how the die fell. You can also consider sum 3, sum 4, sum 5, so on. So not all sums are going to be equally likely. There's only one way to roll the 2, but 6 ways to roll a 7. Now let's talk about counting integers in a range as another example. So consider the question, how many integers are from 5 to 12? Well, the way that we can do that is listing, of course. So we can go with 5, 6, 7, 8, 9, 10, 11, 12, which is going to give me 8 integers. Notice that we can obtain those 8 integers by doing the subtraction 12 minus 5 and adding 1. Because if I just do 12 minus 5, it's just going to give me 7, which is not 8 integers. So the way that you want to approach that is always if you have m less than n, and those numbers are integers, the number of integers between m and n being inclusive, because of course we're including both numbers, is going to be n minus m plus 1. Okay? Now, the plus 1 is going to be critical here because both of the endpoints are going to be included. So this is super important to count that particular extra number. Now, let's apply the counting formula. So we can have, well, what are the 3-digit integers that are divisible by 5? And so we want to know how many integers from 100 to 999 are divisible by 5. And so this goes as multiples of 5. So we can go like 100, 105, 110, up to 9095. And you can notice that this is like 5 times 20 through 5 times 199, which is going to give me this. So you can kind of see that this is a difference between the 20 number multiple of 5 and the 199 number multiple of 5. So we can count all those numbers by making a difference. 199 minus 20 plus 1. And so that's going to give me the total number, which is 180. Now, then we can calculate probabilities, like what is the probability a random 3-digit integer is divisible by 5? Well, first than anything, here we'll be getting the difference between 999 minus 100 plus 1, which is going to give me a total of 900 total numbers. So that's total numbers from 100 to 999. Okay? So, but the event is the multiples of 5. From those we have 180. So the probability here will be 180 over 900. This is the sample space total, and this is the event. So it's super important you're always identifying who's the space and who is and who's the event. All right, so in summary, we have the concept of the sample space where all possible outcomes of a random experiments are occurring. We have an event, which is any subset of the sample space. We define the equal like probability, which is the probability of the event given by the number of times the event occurs over the total number of elements in the sample space. We learn how to count integers between m and n, which is going to be given by the formula n minus m plus 1, and include both endpoints. So like in this interval here. You gotta be very careful of the common mistakes to avoid. Don't forget the 1 when you're counting integers. And when you're applying the formula, this always makes sense when outcomes are equally likely, but when outcomes are not equally likely, then that's not gonna work out. So for example here, if we have this 0 heads, 1 heads, 2 heads with 2 coins, those events are not going to be necessarily equally likely, and we cannot use the probability on that form. It's very important not to confuse event with outcomes. An event is a set of the outcomes, and it can contain multiple outcomes, but it's not all the outcomes. That's the sample space. All right, next, let's see how to do some more probabilities with possibility trees and the multiplication rule.